Welcome to our physics lesson. My name is Purity Anzelimo, and in our lesson we are going to continue with the topic waves 1. That's our topic, waves 1. So far in waves 1 we have looked at the classification of waves, whereby we have looked at electromagnetic waves, mechanical waves, transverse waves, and longitudinal waves. And in our lesson today, we are going to look at characteristics of wave motion. And by the end of the lesson, you should be in a position to state, or you should be able to tell when an oscillation is complete, when an oscillation is complete, and number 2, you should be able to explain terms associated with waves. Terms associated with waves. So when you are given, for example, a wave, and you are told to state when an oscillation is complete, you should be able to show where an oscillation is complete. Then again, you should be in a position to explain the terms associated with waves, to state and to explain. And these terms that we are going to look at, we'll be looking at what we call amplitude. We look at frequency. We are also going to look at wavelength, and we'll also look at periodic time. So those are the terms that we are going to explain in our lesson. So characteristics of wave motion. Now to be able to understand this, we are going to consider an oscillatory motion. By one, we can consider a mass which is vibrating on a spring, moving up, down, up, down. If you attach a mass on a spiral spring and then you displace it vertically a bit, it's going to display a certain motion that we are going to see. Also, we are going to consider the oscillation of a pendulum bob, or when we swing a pendulum bomb, the movement that it's going to portray. So with this, we can say that we are going to explain with reference to an oscillatory motion of a mass attached to a spring or a swinging pendulum bomb. So explained. Explained with reference to the motion of a mass attached to a spring or a swinging pendulum bomb. A swinging pendulum bomb. So in this, we can start with the first one, where we are talking of a mass that is attached to a spring. I'm sure you have learnt about a mass. You know what is a mass. In the previous topic, Hooke's law, you learnt about these masses. Then when it is attached on a spring, when you are defining or verifying the Hooke's law. So here we are going to consider, this is our fixed point, and then here we have a spring. That's our spring. On this end we have a mass attached onto it. So this is our mass. So that's what we have. This is our, we can call this one A. So this is our spring, and here we have the mass. So in this, if we consider this to be our mean position for the mass, this is our mean position at the center of this mass. So if we call this, we can use letters. For example, we can talk of A. So when it is given some vertical displacement, it will swing in this manner. It moves from here up, back again here, again, that's how it will be swinging up, down, up, down. So if we have our A here, so this is how it swings from the mean position up, then down, then. So we have it this way. So if we have this as our, so if we have it this way, so if we have this as our A, then we can have this upper part. If it is moving from A up, then through A, then down, then A, we are going to have it this way. So if this is our A, then this we can call it B, and then here we have C. So how will the mass be moving? The mass will have an oscillatory motion described as follows. So it is going to move it from A here, it will move from A, then it moves to B, then back to A, then moves to C, then it moves to A, then it moves again to B, then it moves to A to C, and the motion will continue. So that is what we are going to have for our motion. But now we want to know, when do we say a complete oscillation is attained? So if it moves from point A, moves to B, through A again, back to C, and then to A, then we'll say that that is a complete oscillation. So we can say for a complete oscillation, we are going to have the following. So if we are taking it from A, we can take it from anywhere, because if we start from B, if it moves from B, they'll move back to A, to C, to A, then to B again. But if we start from A, for a complete oscillation, we'll say a complete oscillation has been achieved when it moves on both sides and then comes back to its initial position. So if it is oscillating in this manner, it's moving up, then through the mean position, down, then back to the mean position, then that is a complete oscillation. So if it is from A, it is going to be A, then B, then back to A, then to C, and then back to A. So that is a complete oscillation. Or if we are starting from B, if it is from B, it can also be B, then it moves to A, then to C, then back to A, and finally to B. That's a complete oscillation. Or, so we can either talk of this or that, or if we are starting from C, it means that it will move from C to A, then to B, then back to A, and then again to C. That is the starting point. So that is a complete oscillation. Hopes you get that. So for a mass attached to a spring, you can see, for us to say that it has moved one oscillation, then it has to go back to its initial position through the two signs. So if it is from A, it has to move to B, then back to A, to C now on the other side, and then back to the starting point. That is now for a mass attached to a spring. Now we want to consider a swinging pendulum bump. A swinging pendulum bump, and see how we can tell that it has completed an oscillation. So in this one, we again consider a fixed point. In this, we are going to use a string to attach. We attach our pendulum bump here. So this is our bump here. This is the pendulum bump. That is the initial position. So if we give it a slight displacement horizontally, so we give it a displacement, it's going to swing this way. So it is going to swing to this direction. We can use a dotted line. So it is going to swing to that side, and again it will swing to on the other side. So we have it that way. So this is our pendulum bomb. Pendulum bob. So this is what we are talking about. If here we have our pendulum bomb. So this is our mean position. We give it a slight displacement. This is our fixed point. We are going to have it move this way. So you can see how it is moving. So if we have our fixed point again at this point, we give it some slight displacement. You can see how it moves. So that is the swinging of a pendulum bob. So it is going to swing. Let's say we have our point A here. We can call this B and this one C. Or to make the contrast, let's use other letters than the one that we have used for the mass. We can use X, Y, Z. X, Y, and Z. So for us to say that it has completed one oscillation. So for one complete oscillation, before we move to one complete oscillation, this is how the pendulum bob will move. So it's going to move from, let's say it's starting from Y. So we have from Y to X, then back to Y, then to Z, to Y, to X, to Y, to Z, from Z to Y, from Y to X, and so on and so forth. So that's how the movement is going to be. So for one complete oscillation, we are going to have the following. So if we are from Y, it's moving from Y, we'll move to X, then through Y to Z, and then back to Y. So that is a complete oscillation. So if we have our pendulum bomb here, moving to this side, back, then this other side, then the starting position, then that is for a complete oscillation. Then if we are starting from X, because we can start from any point, if it is from X, moving to Y, then to Z, then through Y again, and back to X. That is another complete oscillation. Or we can have, if we are starting from Z, it's going to move from Z to Y, then from Y to X, from X to Y, and finally back to Z. So we'll say that that is a complete oscillation. So that is on complete oscillation with reference to the motion of a mass attached to a spring or a swinging pendulum bomb. So that's what we have. So I want us to move ahead and consider if the mass takes, or maybe the pendulum, if the mass takes 2 seconds to complete one oscillation. If the mass takes 2 seconds to make one complete oscillation, I want us now to have a sketch of a displacement time motion that is for the wave. So we have the displacement time graph for the motion. The displacement and displacement, we will draw a simple sketch for how the motion will be like. So it is a displacement time graph. So on the vertical axis, that is the y-axis, we have displacement. So we name this is our displacement against time. So here we have time in seconds, and we have been told that it takes 2 seconds to make one complete oscillation. One complete oscillation. So we can mark here and say, let's say this is our, we mark it, that is on the column of the seconds. So we have here 1, 2, so we can have it that way. Then we can mark on these two signs and see. We can mark on the other side. So we want our wave to be up to here. And on this other side, here. So this is just to guide us. So we want to plot that wave. It is making one complete oscillation in 2 seconds. So if this is our 1 second, 2, 3, 4, 5, this, and we have our mean position at this point here, then we are going to have our wave as follows. So we have it, we have our wave this way. We want it to make one complete oscillation in 2 seconds. So you can see from this position we have the first part, the crest, the trough. So we have now one complete oscillation up to there, taking 2 seconds. We can continue with plotting the wave. So we have it moving this way. And that way, and it continues. So that is our wave. We can make it as smooth as possible. So this is 2. So you can see clearly that in one complete oscillation, the time taken is 2 seconds because this is our complete oscillation. So I want us to consider this wave. So this is what we have. This is the wave. These are 2 seconds. So you can, maybe I can ask you to count how many complete oscillations or how many oscillations can you see in this wave? What's the number of oscillations in this wave? How many are they? We can count them. We are having 1, 2 and a half. So we have 2 and a half. These are 2 and a half oscillations. So hope that is clear. So from this wave and displacement time wave, we want now to look at terms associated with waves. So this is a sine wave. This is actually a sine wave, as you can see. So that is the crest alternating with the trough, crest, trough, crest, trough, and so on. And of course, also when you are plotting these curves, ensure that it's a smooth one, just like in mathematics. We say that the turning point should be clear. So for a wave, it turns, and we have it this way. So this is our 4, 3. So this is the turning point. So when you are drawing this turning point, ensure that it turns. So don't draw it like this, but it should turn. It is a curve. So from this, we want now to look at the terms associated with waves. Terms associated with waves. If you follow keenly, you will understand it so well and you'll be in a position to solve the numerical problems in an easy way. So we look at terms associated with waves. So we start by listing them down. We'll discuss the following terms. Number 1, amplitude. amplitude is denoted by capital letter A. Number 2, we look at frequency. Frequency is denoted by a small letter f. So for amplitude, a capital letter A, frequency, a small letter f. Number 3, periodic time, denoted by a capital letter T. And finally, on terms, we are going to look at wavelength. Wavelength is denoted by a Greek letter lambda. This is how we write it, that way. Lambda. It's a Greek letter. So wavelength is denoted by a Greek letter which we are calling lambda. So those are the terms that we want to discuss with reference to the wave that is here. So we have this wave, we want to discuss these terms. So we'll start with the first term, which we are talking of as the amplitude. So what is amplitude? When we talk of amplitude, it refers to the maximum displacement from the mean position. It is the maximum displacement. It refers to the maximum displacement from the mean position on either side. So like in our wave here, this is our mean position. If we have this is our mean position. Now, our maximum displacement will simply mean the highest point on either side, either here or here. So for this, let's say our displacement was in meters, and here we have this one as 0.1, and here we have negative 0.1. So it means that our displacement from the mean position is 0.1, and that is the amplitude. So from our sketch here, we can say that amplitude will be equal to 0.1 meters. I would like also you note that the SI unit of amplitude is meters. The SI unit is meter. Being a displacement, and we know that the SI unit for displacement is meter, the SI unit of amplitude will be meters. So that is the SI unit of amplitude, and we are saying that it is simply the distance from the mean position. So if you are given a wave like this one, and you are told what is the amplitude, you simply come and check the highest point. So you look at the crest or even the trough, and you assume this negative now when you are giving the amplitude, because it is now the distance from the mean position. So we are going to have 0.1 meters. So if it were in centimeters, we need to convert it into meters so that we can give in its SI unit. Let's move on to our second term, which is frequency. How frequent? Now in English, how frequent? Now when we talk of frequency, it refers to the number of complete oscillations in 1 second. It is the number of complete oscillations in 1 second. We now know what is an oscillation. So we think that if we have a transverse wave and it moves from this point down up to the same position, then that is a complete oscillation. So the number of those complete oscillations in 1 second, we refer to it as frequency. And the SI unit is hertz. The SI unit is hertz, which we write as this. The SI unit is hertz. So if we come to our wave here, and we want to know what is the frequency of this wave, and we are saying that frequency is the number of complete oscillations in 1 second. So in this wave, we have 1 second here. So the number of complete oscillations in 1 second. So we want to see what is the frequency here, because we can see here we are having how many oscillations are these before 1 second? This is half of an oscillation. It is a half. And therefore, we'll say that the frequency is a half, because in 1 second, we have half of the oscillation. And we are saying frequency is the number of complete oscillations in 1 second. So in our question here, the frequency is equal to a half, which is 0.5 hertz. That is the frequency. The number of complete oscillations, in our case, the number of oscillations here are a half, and therefore the frequency is a half. Or we can approach it this way. How many oscillations do we have in total? 1, 2, 2.5. So we can come and say that we have 2.5 oscillations, and they are covered in how many seconds? In 5 seconds. So we ask ourselves, what about in 1 second? How many oscillations are these? So we'll just come and cross multiply. So we have 2.5 times 1 divided by 5. 2.5 times 1 divided by 5. This will be the same as 25 divided by 50, which is 0.5 hertz. It is the same as this. So that is what we refer to as frequency. Let's move on and look at periodic time. Periodic time, we are still referring to our wave here. Now when we talk of periodic time, it is not the time taken to complete one oscillation. Time taken to complete one oscillation. It is the time taken to complete one oscillation. And the SI unit is seconds. Being time, the SI unit for time is seconds, and therefore the SI unit for periodic time is seconds. So we are saying periodic time is the time taken to complete one oscillation. Like for example, if we come back to our question here, to complete one oscillation, how many seconds are there? So we have one oscillation from here. If we start from here, this zero, here we have 0. So we have from here, our complete oscillation is up to here. So how many seconds are there? We have 2 seconds. We can even start from here. If you want the oscillation, we can start from here. For a complete oscillation, so we have it to here, 4 minus 2, which is 2. So we can say that our periodic time here is 2 seconds. The periodic time is 2 seconds. It is the time taken to complete one oscillation. Time for one oscillation is what we are calling the periodic time. And now I want us to see the similarity or some relationship that is between periodic time and frequency before we look at wavelength. Some relationship between periodic time and the frequency. Relationship between periodic time T and the frequency F. Now, from our wave here, we have been able to see that the frequency is 0.5 hertz and the periodic time is 2 seconds. That's what we have been able to see. Our frequency, number of oscillations in 1 second, we have 0.5, and we have also been able to see that the time for one oscillation is 2 seconds. Now, if you look at this, if we were to find the reciprocal. If we were to find the reciprocal of frequency, 1 over the frequency, we have 1 over 0.5, which is equal to 10 over 5. 10 over 5 is 2. Look at it. The reciprocal of frequency is 2, and 2 is the periodic time. Again, the reciprocal of periodic time, which is 1 over 2, is 0.5. And 0.5 is our frequency. And therefore, we can make a conclusion that periodic time is the reciprocal of frequency. And vice versa, frequency is the reciprocal of the periodic time. So when you have frequency and you want the periodic time, you just get the reciprocal. So the periodic time is 1 over f, and frequency is 1 over the periodic time. So you need to make note of that. So when you have one of them, when you have the frequency, you can get the periodic time, and when you have the periodic time, you can get the frequency. Is that clear? So finally, our last term, we have wavelength. Denoted by lambda. Wavelength. Those are two ones. Wavelength. So when we talk of wavelength, it simply refers to the distance covered in one complete oscillation. So in this one, we are going to consider a different wave, but we can start by defining. We are saying that this is the distance. We are going to give several definitions. It is the distance covered in one complete oscillation. Or we can say that it is the distance covered between 2 points which are in phase. It is also the distance covered, or distance between we can also say that it is the distance between 2 successful crests, or 2 successful troughs, or even 2 successful rarefactions, or 2 successful compressions. So we can define it further. All those are definitions for wavelength. You can give any of them. So we are also saying that it is the distance So we'll see that in an example of a wave, the sketch for a wave. So we are saying that wavelength is the distance covered in one complete oscillation. We can also say that it is the distance between 2 points in phase. It is the distance covered between 2 successful troughs. So if you have 2 troughs following each other, the distance between them, or even crest, distance covered between 2 successful compressions or rarefactions, that is for a case of a longitudinal wave. Then, being a distance, therefore we can say that the SI unit is meter. The SI unit is meter. So I want us to consider this wave. So here we are having a transverse wave. They can be seen. Now that the vibration of particles is it's at right angle to the direction of wave travel. So this is a transverse wave. So here we have displacement. And here we have distance. We can say in meters. So we have, this is our starting point. This is displacement in meters. Here we have 0.3 negative, and here we have 0.3. So here is 0.3. So we have our wave. I'm going to draw the transverse wave and be able to define wavelength. We can have our wave up to there. So these are our turning points for the wave. So that's our wave. So we can start with the first definition. So if we have this as our 0, 2, 4, 6, 8, 10, 12, 14. So we are saying that it is the distance covered in one complete oscillation. So you just come from whichever point you see where we have a complete oscillation. For example, from here up to here, that's a complete oscillation, and therefore our wavelength is 8 minus 0, which is 8 meters. It's in meters. So the wavelength is 8 meters. Or we can say that it is the distance covered between two successive troughs or crests. So for example, if we consider troughs, we can start with crest, this crest, and this other one here. So you just come and read here. Here we have 2. Here we have 10. So 10 minus 2 is 8 meters. Again, two successful crests. So this is a crest. We don't have another crest, but we can complete this one and see so that we can explain. So here we have 14. These are troughs. These are two successful troughs, this one and this one. So here we have 14 minus 6, which is again 8 meters. Again, we are saying that it is the distance covered between two successful compressions or rarefactions. That is for a case of a longitudinal wave. And I can explain this way. If we have a longitudinal wave, we say that it has sections of compression alternating with rarefaction. So we can have a longitudinal wave. So we can have it this way. So this is what we are talking about. So when we are saying that it is the distance covered between two successful compressions. So if we have the distance from in between here, this is a compression, and in between here, this distance is what we are calling a wavelength, or the distance between two successful rarefactions. So we have the distance in between this rarefaction here and the other rarefaction. So this distance is what we are calling a wavelength, or simply the distance in one complete oscillation. And for this one complete oscillation will be as a result of this and the rarefaction. So the compression and the rarefaction, just like when we have a crest and a trough, that is a complete oscillation. So again, from here up to here, that's a complete oscillation, and that gives us one wavelength. So that is on wavelength, and we have been able now to define all the terms. We are going to use them in numerical calculations, very, very key. Again, in Form 3, in waves, you'll also be using these terms that we have just looked at. So we have looked at 4 terms. We have looked at amplitude, and we've said it's the maximum displacement from the mean position. Frequency, number of complete oscillations or number of oscillations in 1 second. We have also looked at periodic time, time taken to complete one oscillation, and finally wavelength, and we have given it all these definitions. And we have seen that if you are told to explain what is wavelength, you can give one of them. Simply says the distance covered in one complete oscillation. So in our next lesson, we'll now relate speed with the frequency and wavelength, and we'll be able to derive the wave equation and use it in numerical problems, whereby we are going to involve all the terms that we have learned plus the other term which we are going to look at, which is speed or the velocity of a wave. So I'd like you to do the following. So those are the questions. Number 1, explain the following terms giving their SI units. 1, wavelength. 2, amplitude. 3, frequency. And 4, periodic time. Then 2, write the formula showing the relationship between periodic time and the frequency. So in our next lesson, we'll now derive the wave equation. Thank you.